Greetings, everyone. This is Mr. Pryor. You are in general organic and biochemistry or fundamentals of chemistry. Thanks for joining me. We are in chapter 5. Camera's not working, which might be a good thing. What we need to focus on is the work and the information. This chapter is titled Gases, Liquids, and Solids. We will start in that order. Gases will be the first subject matter. So when we look at this, the title of the slide is gas pressure. Pressure is kind of, try to think about it philosophically. You have pressure that pushes in and you have pressure that pushes out, okay? So typically pressure is measured by what is pushing out, okay? What's pushing up against the balloon, or what's pushing on the container, what's pushing in the cylinder. So, but you also must remember we have pressure from the outside of a system pressing inward. But usually in our measurements, we have pressure from inside a cylinder, inside a balloon, inside a device, inside a glass container that is pushing outward. So, pressure is force per unit area exerted against a surface. They use millimeters of mercury, which you think, well, what's happening here is we're using a height, which is translated in a device. The pressure creates the height of mercury, which correlates to a pressure, be it atmospheric pressure or torr. For example, millimeters of mercury. And that's a very interesting, maybe even somewhat complex thing to understand. This device that can measure millimeters of mercury, it's completely coordinated with 1 atmosphere equals 760 millimeters of mercury. That's not something you can typically do at home unless you're very good with crafts and you can come up with this device on your own. You might be able to, but it would be a lot of work for most of you. So bear with me that 1 atmosphere equals 760 millimeters of mercury. That is a given. Translating that, also it equals 760 torr. So now you've got 3 equivalent definitions basically of atmospheric pressure. So of course, indirectly, 1 torr would equal 1 millimeter of mercury. Okay, that's not stated here. I'm just taking it to the next step. It's okay to think past what you see on the slides. What did I post on the right and the left? These are nice tools that we can find in Google. Google is just a great reservoir of information. These conversion factor tables where you can double check your work online, and these are useful. So I recommend you trying Google and finding these nice little calculating devices that can give you these values. If you ever work in engineering, or you're a nurse, or maybe even vet tech science, you may work with things that give you values of pressure, and pressure can be from gas, it can be from liquid. Presently, my position and job has me looking at all sorts of water filter devices and pressure readings, primarily for liquid, but also for gases. And what does it say here? We also have some other definitions. 1 atmospheric pressure equals 1,001 and 325 pascals. Okay. Then another definition of atmospheric pressure is 1 atm equals 29.92 inches of mercury. Okay. We also have bars, or barometric pressure, or bars of pressure. 1 atmosphere equals 1.01325, which is the value. You see that over in the left-hand visual that I give you. And at the right hand, you see the very top definition of atmospheric pressure. Atmospheric pressure is measured using a barometer. Okay, the pressure of a confined gas measured using a manometer. So just remember primarily, and let's move on to the next slide. Just remember primarily, we are talking about things that push outward that are being measured from inside the cylinder. What is the pressure inside the unit, inside the cylinder? Because we have pressure on the outside pushing in, and we have pressure from the inside pushing out. And what are we measuring? Typically, what's relevant to the cylinder? What's relevant to the device? What's relevant to the glass flask that may be under pressure? There's specialized glassware that can handle pressure. That's a big thing in organic chemistry. You can make one of these mercury, well, I wouldn't use mercury, of course. You can make a barometer. You wouldn't want to use mercury. That would be obviously dangerous. Mercury is something that binds to some of our enzymes irreversibly. And here we can see heights in millimeters, atmospheric pressure pushing down upon the liquid mercury, pushing up the mercury into a capillary tube or a tube where there is a quote unquote vacuum. These vacuums can be engineered so that they are kept under vacuum, that there isn't air leaks. This is a simple device that you can come up with on your own. Like I said, don't use mercury. That's very dangerous. Very dangerous. Not something you ever want to interact with physically. Gas pressure. Here is a small cartoon showing a device of how air can come in from the atmosphere using a stop valve. And then you can see where the gas sample is pointing an arrow. For example, the gas comes in here as I move along with the cursor, goes into the circular area, and it is able to then push up this liquid. And again, it's mercury. And you can measure the height that the mercury is pushed up, 80 millimeters. And so that can correlate with, as we learned, 1 atmosphere of pressure equals 760 millimeters of mercury, or 1 atmospheric pressure equals 760 torr. So these values are important. So let's go on to the next slide. Laws, gas laws, very useful to help us understand gases, the basic physical concepts of gases. Boyle's law. For a fixed mass of gas at a constant temperature, the volume is inversely proportional to the pressure. Meaning the higher the pressure, the smaller the volume. The lower the pressure, the higher the volume. Okay. So go ahead and think about that. There's many ways to think about this. This is where introductory students get confused because they have an idea what pressure means. You know, are we talking about a fixed cylinder? Are we talking about a fixed volume? Are we talking about the cylinder changing? Are we talking about the volume changing? So these things can confuse students. I sometimes say, go ahead and plug in numbers into P and V1, and then say the pressure and volume change. The pressure changes. What happens to the volume? For example, you could say pressure 1 is 1 atmosphere. The volume is 10 liters. Now the pressure goes to 2 atmospheric pressure. What would the volume be? Okay. Think about that. Charles' law: for a fixed volume of gas at a constant pressure, the volume is directly proportional to the temperature in Kelvin. So what they're saying, this volume to temperature ratio is a constant. So if you change either one, if you change the temperature or if you change the volume, they will both change in proportion. They're not inversely proportional. So if the volume 1 is, say, 10 liters and the temperature is 273 Kelvin, and then say that the temperature goes up to 373 Kelvin, what would the new volume be? Okay, that's something you can think about. Let's go on to the next slide. So Boyle's law and Charles' law, PV equals PV1 times V1 equals P2 times V2, and then you have Charles's law with volume over temperature. Okay, so those are different. They're now putting them together. Can we put these together? Well, here comes the Gay-Lussac law for a fixed mass of gas at constant volume. Notice they don't show the volume. They're just telling you that there's assumptions in these laws. The pressure is directly proportional to the temperature in kelvins. So we have pressure 1 divided by temperature 1 equals pressure 2 divided by temperature 2. So if the temperature goes up, the pressure goes up. If the pressure goes down, the temperature likely went down. Okay, you can test that to see if that holds up. With the calculator, just put in numbers. You don't even have to write everything out. You can just put in numbers sometimes. Now on a test, of course, I would say write things out. But if you're just learning, use the calculator, put in numbers, make up numbers, and see what happens in this equation. For example, have one unknown. For example, if we take Boyle's law, you could say, I know pressure 1, I know volume 1, I know pressure 2. Well, what would volume 2 be? Well, what would volume 2 be if these values change? And so on, and so on. And you can try this in different ways. Charles' law, the same thing. Gay-Lussac law, which we just talked about. And so we can put all these together. And here they give you some constant. There's a hidden constant in this. The constant with Boyle's law would be the temperature. The constant with Charles's law would be the pressure. And with the Gay-Lussac law would be volume. Okay. And when they say constant, it really is the relationship that doesn't change. The numbers may change, but the values are roughly correlated to each other. So let's go on to the next slide. Boyle's law, Charles' law, and Gay-Lussac law can be combined to give you the combined gas law. So pressure 1 times the volume of 1 divided by the temperature of 1. Or we could also look at this as a time component. We can say the initial pressure of some solution or gas at some initial volume divided by an initial temperature, then can change, and then we get a pressure at a later time versus a volume at a later time, divided by a temperature at a later time, assuming some of these or all of these probably changed. And that's the combined gas law. Here is an example of the gas law calculation, and this is a really good place to start. A gas occupies 3 liters at 2 atmospheric pressure. Calculate its volume when the pressure becomes, it increases here, 10.15 atm at the same temperature. Now, you might say to yourself, they don't give us the temperature. How do we handle this? Well, they're telling us that the temperature initially is the same as the temperature after these changes in the pressure. And then how does the change in the pressure create a change in the volume? So what we can do, we can write out this combined gas law. We can rearrange to the variable we don't know. And you might say, well, we don't know what temperature 1 or temperature 2 is. Well, we know they're equal. Okay, so really we could start off and just cross out T1 and T2 if we'd like. Okay, that would be good enough. we would likely have Charles's law, but we can use the combined gas law as well. So we can cancel out the initial temperature with the corresponding temperature with the change in pressure, which is the same, whatever that number is, whether it's 300 or 30, it'd be in Kelvin. Now, Kelvin, remember, you add 273 degrees to any temperature that's in Celsius to get Kelvin. We practice that. You guys are very good at that. We want to get volume 2. The pressure increases. So you think about this intuitively. Do you think the volume will increase because the initial pressure was 2.0 atmospheres? The volume for that under the constant temperature, even when we change the pressure, it'll be under the same temperature. It's only the pressure changing. The volume was 3.00 liters initially. We increase the pressure, we probably decrease the volume, and that's what we get. Our calculation tells us the new volume 2 is 0.591 liters when we increase the atmospheric pressure from 2.0 atm to 10.15 atm. Now, for some of you who are engineering conscious, this is probably a device that somehow increased the pressure. Maybe you can increase the pressure maybe by shrinking the volume, by forcing more air in, by using some type of plunger. There's many ways to increase the pressure. This is a very generic example, but it has real world applications. Gas laws. Again, Avogadro's law. We talked about Avogadro's number, which is 6.022 times 10 to the 23rd, but now we're talking about Avogadro's law, which is a little bit different. Equal volumes of gas at the same temperature and pressure contain the same number of molecules. Okay, let's say that one more time. Equal volumes of gas at the same temperature and pressure contain the same number of molecules. So the actual temperature and pressure at which we compare two or more gases does not matter. For convenience in making comparison, chemists have selected one pressure as a standard pressure and one temperature as a standard temperature. So now we're getting into these definitions of STP, standard temperature and pressure, because we'll see that all these constants have been calculated in a lab that give us information about different gases, and to be able to have everything on the same page, you want a standard temperature and pressure. So that's what they do, is they selected 0 degrees Celsius, which is 273 Kelvin, and 1 atmospheric pressure. Okay, so you got to realize, for us common folks, it's probably difficult to get these standardization temperatures, but we can work from that. Okay, we can work from that. Basically, they're telling you that's the same number of molecules. It affects these volumes and temperatures. So there's an assumption, of course, that the number of molecules doesn't increase or decrease. It's the same. But of course, the volumes and temperature, that could change. So all gases at STP or any other combination of pressure and temperature contain the same number of molecules in a given volume. But how many molecules is that? So now we go back to the number we once learned. 1 mole contains 6.022 times 10 to the 23 formula units, meaning that could be molecules. We're not always talking about individual atoms. We may be talking about molecules. So be careful that you don't just look at the atoms or elements that you think about. Is 1 mole talking about how many molecules we have, or is 1 mole talking about how many elements we have? We could figure out both, right? We can figure out, if we know how many formula units we have of a molecule, we could figure out how many carbon formula units exist in that molecule. So what volume of gas at STP contains this many molecules? This quantity has been measured and is 22.4 liters. Okay, 1 mole of such quantity of gas equals 22.4 liters at 1 atmosphere. Thus, 1 mole of any gas at STP occupies 22.4 liters. So at 0 degrees, so at 273 degree Kelvin or 0 degrees Celsius at 1 atmospheric pressure, any mole of an ideal gas being following a definition that we'll talk about, occupies a volume of 22.4 liters. Okay, and that's standardized. Think about that. Let me know if you're struggling with that. The ideal gas law, Avogadro's law, allows us to write a gas law that is valid not only for any P, pressure, V, volume, and temperature, but for any mass of gas. Because for one, we would know the moles, then therefore if we know the moles, we can probably figure out the mass or the weight, which weight and mass are not always the same, as you learned in your first chapter of this course. So this is something you want to remember. PV equals nRT. And you can get a lot from that. Now you're throwing in moles. You've learned what moles are. You've learned now what STP, standard temperature and pressure, equals. And you've learned that at STP, the volume of any 1 mole of gas is going to be 22.4 liters in terms of volume. So there's a lot of assumptions with ideal gases, such as there's not strong interactions between the molecules, okay? There's not these interactions that make the gas increase or decrease because of the interaction between the individual molecules in the gas. And a lot of times we're starting off simple. We're starting off with one type of gas, one gas only that's completely purified, in some kind of cylinder or tank or some kind of experimental apparatus. In the real world, we have multiple gases in our atmosphere, but this is a good way to start. We're building a model so we can understand science. PV equals nRT. We know P equals pressure of gas in atmospheres, V equals volume of gas in liters, N equals moles of gas, and temperature, T, is in Kelvin, where we add 273 to get that number if we're dealing with Celsius to get into Kelvin. R is an ideal gas constant, a constant for all gases. Now, just to let you know, if any of you are thinking, well, this probably doesn't always hold up, you're absolutely right. Because we're going to ignore things like attractive forces between gases. And many times gases are, and we can do this because a lot of times gases are so far apart, they don't interact close together, and their interaction and forces between each other are minimized, right? Of all the forms of matter we talk about in simple terms of gas, liquids, and solids, gases, the molecules are spread the farthest apart. So of course, it is probably the easiest thing to do is assume there's no interaction between individual molecules. Okay, and that's not something we can typically do we can't do that in solids and liquids. Okay, not typically. Last slide. Ideal gas law. We find the value of R, and how do we get this constant? And when we get this constant, is R for all gases? No, it's for ideal gases. Ideal gases being these gas molecules that don't interact with each other. It's a pure form of gas. Well, not always. We'll find out we could actually have solutions of gases, and the ideal gas law will still work. But those gases don't interact with each other, so it's as if they're the same gas, because they have no intramolecular interactions that we have to account for. Here's the problem. We make the pressure 1 atmosphere. We know the volume will be 22.4 liters for 1 mole of that gas at 0 degrees Celsius or 273 Kelvin, which is the number we need for these equations. If you put in 0 Celsius, you will have an equation that's unsolvable. You will have 0 in the denominator. Here we then come up with the R value of 0.0821 liters times atmospheres divided by moles times Kelvin. So that's kind of a complicated unit to come up with, but try this, see if you get those units. Make sure you don't confuse numerator and denominator units. Here's a problem for you. See if you can get the answer that they come up with, which is solve the temperature. This is kind of neat because you can have the pressure, the volume, the number of moles, the R value, and then you can find out what the temperature of the gas will be if it's an ideal gas. This wouldn't work if it wasn't an ideal gas. And this doesn't work for liquids either. So if you try to use this equation for liquids, that would not be a wise thing to do. I don't know how far you would be off or how close you would be, but it's meant for gases. 1.0 mole of CH4 gas, methane, occupies 20 liters at 1.00 atmosphere. What is the temperature of the gas in Kelvin? So they're giving you the volume here. That's the size container. You might say, well, why isn't it 22.4 liters? Well, they've changed something on you, okay? They've shrank the container, or they shrank the volume that they want you to assume it was in. You can think of it as a container if you like. And so you get these variables that they give you. You plug these numbers into the equation. You rearrange the equation to solve for temperature rather for R this time. You should be able to do that. And you're able to find that the temperature here, we have a more compact volume of 20.0 as opposed to 22.4. And so we see here, what do we get? We get a lowered temperature. It's 244 Kelvin now. And go ahead and work with that and see if you can understand what's going on there, and try to think about that. Why? Okay, it's less volume, but all these other factors are going to be the same. So if it's less volume, then if it's still going to act the same, then it must have probably a lower temperature because it's not expanded at the volume of 22.4. These things are indirect. You have to think a little bit about them and kind of come up with your own correlations. And I thank you. This is Mr. Pryor. Good luck and take care.